Hello everybody, this is Dr. Christopher White and welcome to part 2 of streams and flooding. Alright, so now we're going to think about the properties of the streams or rivers themselves. Okay, so to begin with, let's think about how the water is moving. So the first type of method through which the water can move in a river is through laminar flow. So laminar flow occurs in rivers that have smooth banks and beds. So if we look at this river here, you can see the banks of the river are going to be quite smooth, the bed of the river is also going to be quite smooth. Well, that means there's nothing to impede the flow of the water. So the water just takes a nice, straight, easy path. It means the water will run smoothly and the river will naturally split into different layers. And these different layers will actually sometimes move at different velocities as well. There will sometimes also be friction between the layers, which will help to, which will sometimes make a layer slow down. So you might have actually experienced this particular phenomenon of laminar water, and it's the kind of thing that you might experience in the Houston area in the spring if you've gone into a swimming pool. So it might be you might have a situation where the water has been heated up by the sun, so the water at the top of the swimming pool is quite warm. So you've formed a distinct layer of warm water at the top of the swimming pool. So you stick your hand into the swimming pool, the water feels warm. So you think, great, I'll go for a swim. Then of course what happens is you jump off the side of the pool into the water, you punch through that very warm layer of water at the top, and you suddenly hit a bigger layer of much colder water below. So that would be a very crude example of lamination in a body of water. Now, the other type of way through which water can move is through turbulent flow. So turbulent flow is produced in environments where you have a very rough riverbed. So you can see it here in this picture. You can see this particular riverbed is full of boulders all over the place, and you can see how the water is churning. So in a turbulent environment, the flow is swirly and it contains lots and lots of eddies. And that's because there are lots and lots of obstructions in the way. And that stops the water from taking a nice, smooth path in just one direction. It means the water has to move around these obstructions. It produces these eddies, and it also causes the water to swirl around quite a lot. And so it produces quite a chaotic flow. So typically, meandering rivers will have a nice laminar flow. Turbulent rivers are commonly associated with both straight and braided river systems. So okay, now we've already looked at this, so we're going to breeze over this slide relatively quickly. But now we need to think about the solid component of the streams, the sediment actually being moved by the water. Well, as we know, there's a few ways in which sediment is moved by the water. The first way is as the bed load, and this is the material that's along the base of the river down here. This material is often sand and gravel sized. So the bed load contains material which cannot be picked up by the water because it's too heavy. The material of the bed load will be moved in one of two ways. It can be moved by traction. Traction is when large particles, so gravel and sand sized clasts, are rolled, slid or dragged along the bottom of the river by the flow of the water. The other method by which material can be moved as part of the bed load is through saltation. And that's typically when sand-sized particles get temporarily picked up by the river. So the water picks them up temporarily and then drops them. It picks them up, drops them, picks them up, drops them. So these particles will move through a leapfrog motion along the riverbed. So bed load, sediments transported as either traction, by either traction or saltation. Next is the suspended load, and this is typically clay and silt sized clasts. They are so light that they can be suspended in the water. So as long as the water is moving, the clasts will be suspended in that water. So essentially that's why water in rivers like the Mississippi looks so murky. It has that kind of brownish grey colour to it, doesn't it? And that's all those clay and silt-sized particles essentially suspended in the water. The final method through which a river moves material is in the dissolved load. And this is in the form of ions dissolved in the water. So classic example of that is, once again, take a glass of water, put a spoonful of salt in it, the salt disappears and dissolves, doesn't it? The salt has split into sodium and chlorine ions, and they have essentially dissolved into the water. It's the same process with minerals and bits of rock. The minerals within those rock will dissolve, and their constituents will dissolve into the river water. Okay, so rivers will move sediment as either part of the bed load, suspended load, or dissolved load. And if your sediment is part of the bed load, it will be moved by either traction or saltation. All right, so the next thing we need to think about is something which is referred to as discharge. So discharge is simply the amount of water, so a volume, flowing over a certain point in a given amount of time. Now, discharge will vary with time, and those changes will mostly reflect changes in the seasons, for instance. So obviously in the, you would expect in the fall and the spring especially, you expect those seasons to be quite wet. So you would expect discharge at those times of the year to be higher. In the case of summer and winter, normally you would expect discharge to be a little lower. And so you'd expect the discharge, so the amount of water being added to rivers to be slightly lower. And so the discharge should also be slightly lower. Discharge can also change on a daily basis as well, or even an hourly basis. In the Houston area where we are, we're very familiar with very, very large thunderstorms. And a very, very large thunderstorm will, of course, dump a huge amount of water into a river very, very quickly. And that addition of substantial quantities of water very, very fast will, of course, increase the discharge. Once that water has moved through the system, the discharge will return back to normal. So discharge is a variable thing. It's not a constant for a river. So discharge is typically measured in cubic meters per second. So how many cubic meters of water are moving through a point every second? And it's calculated by a very simple formula. We calculate it by multiplying the cross-sectional area of the river by the river's velocity. So the equation is down at the bottom here, Q. So Q essentially equals the stream depth multiplied by the stream width, that's our area, multiplied by the stream velocity. So it's a very, very simple calculation. Now, how we actually get to this stream area is actually a little bit more complicated than this formula would actually suggest. And we're actually going to be dealing with this as part of the lab. So velocity is obviously measured as a distance unit over time. So typically feet per second, meters per second. Obviously, if we're doing it from a scientific point of view, it's going to be metric, so it would tend to be meters per second. Now, the velocity is of course dependent on the gradient. We've already discussed this. The faster your water drops, typically the more energy it will have. So changes in elevation over distance will affect the velocity. So in this case, don't worry about the feet per mile or meters per kilometer. So a high gradient typically produces a high velocity, and that's not really a huge shock because your water is dropping very, very fast. So, if you've ever been on a roller coaster, you'll know as you come to the top of the roller coaster, right at the peak, and then you drop down. As you start dropping down that very steep slope, the velocity is quite extreme. Then, of course, you come to the bottom, you slow down, and then you'll go up. Typically, you'll go up a much more gentle slope and a much more gentle decline afterwards. When you're going up that gentle slope and coming down the gentle slope, you'll notice the velocity is considerably lower. So essentially the gradient obviously affects your velocity. Another thing that will also affect velocity is channel shape and roughness. So the geometry of the channel, its morphology, so its shape, and the bed load, the material in the stream, that will also affect the river's speed. So let's have a think about channel shape and roughness. So here are a few things. So both affect stream velocity due to drag. So narrower, deeper channels allow for faster flow. So meandering rivers where the channels are typically deeper and narrower will tend to channel water faster. In contrast, the type of channels we get with braided rivers, which are wide and shallow, they actually tend to bring the velocity down. Another thing is nice smooth channels tend to give a much faster flow because the flow is not being impeded. In contrast, rough channels like this one here will actually have lots of impediments, and all those impediments will help to slow the water down because the water has to go around them. And also think about the water itself. It's constantly moving past them and rubbing against them. So there's also the question of friction. So in this situation, the surface area that the river is actually touching is quite low. So there's much lower friction. In this situation, even though this channel is approximately the same shape as same size as this one, it has all of these extra particles at the bottom. And the water is not only rubbing against the margins of the river, but it's also rubbing against the surfaces of all of these large particles. So the surface area which the water is in contact with is much, much larger. And so what you really want for maximum velocity for your river is a nice straight channel, okay, where you have nice smooth sides and the channel itself is quite narrow and deep. In contrast, for reduced velocity, you're going to have a situation where your channel contains lots and lots of material in the bottom of it, and your channel is quite wide and quite shallow. So, shock horror, although this doesn't seem to make sense, the velocity of meandering rivers can actually often be in excess of that of braided rivers. So remember, braided rivers are forming in mountainous terrain, so you'd expect them to have more oomph. However, most of the time, the quantity of material in the bottom of a braided river and the shape of the channel of a braided river will actually make the water move more slowly. In contrast, a meandering river will often be able to move material a bit faster because it has a nice smooth channel, and that channel is quite narrow and deep. So bear that in mind. I know it seems counterintuitive. You would expect the river in the mountainous terrain to obviously have the higher velocity, but it doesn't always. So gradient also affects discharge. So discharge increases closer to the base level. So the discharge of the river gets higher as you approach the river's mouth. Now, once again, this might seem a little counterintuitive because you expect the water up here in the mountainous terrain to be flowing really, really quickly. And that means in theory you would expect lots and lots of water to pass through a point very, very quickly because the water is moving so fast. However, in reality, as you come down here towards the mouth of the river, well, what's happened? Number one, the river channel has become narrower and deeper. It's become smoother. That's going to help improve velocity. And you've had more and more water being added to the channel. Because as you go from the mountainous terrain towards the mouth of the river, you have all of those tributaries coming into the river, don't you? They're adding extra water to the river. And obviously, as you add extra water to the river, well, the volume is going to start increasing, isn't it? So remember, discharge is volume multiplied by velocity. So as you head towards the mouth of the river, you have more water in your river, meaning larger area. And at the same time, your river channel becomes narrower and deeper and smoother, meaning you have a higher velocity. So discharge increases, area increases, velocity increases, so discharge increases. So when it comes down to it, the discharge is highest towards the river's mouth and typically lowest towards the river's head where it starts forming. I did not mean to do that. Let's just skip that down there and go back to where we were. Okay, so the next thing to think about then is how does our stream actually change downstream? So as our river comes from its head, all the way up here where the river starts, to its mouth down here where it ends, how does our river change? Now what you can see here is we've selected certain parts of the river and we're going to look at what's happening to them downstream. So we have T1, T2 and T3, 1, 2, and 3. These are our tributaries going into our main channel. Okay, we have the headwaters, which are marked out here by letter H. We have a delta marked out by D and a mouth marked out by M. Okay, so we're going to have a look at how things are changing as we head downstream. Okay, so first of all, water depth. Well, this one isn't a huge shock. So as we've discussed, as you come downstream, you get more and more water being added to your channel. That means you have a greater volume of water, so your river channel naturally has to become both deeper and wider to accommodate that additional water. So as we move from the headwaters to the mouth of the river, the channel depth will increase, channel size should I say, will increase because it has to get deeper and wider to accommodate the extra water. What about the water velocity? Well, we've already discussed this. Okay, up here in the headwaters, you typically have a lot of channels which are quite shallow and wide and full of obstructions, so the velocity is actually relatively low. In comparison, as you come downstream, the channels themselves typically get broader, narrower, and have fewer obstructions, so the velocity actually increases. Then we have discharge. Remember, discharge is simply the area of the river multiplied by the velocity. So if we look at this situation, we can see as we head downstream, the channel gets both wider and deeper, so its area increases. At the same time, the velocity is also increasing, and discharge is area multiplied by velocity. So unsurprisingly, the discharge is going to increase. Next we have the total sediment load, so how much sediment is actually being carried by the river. Well, up here in the headwater, the river itself is not actually going to be that big. It's going to be quite a narrow channel with not much water in it. So that river, yes, it can transport quite large sediment because it's quite energetic water, but because there's so little water there, it's not really transporting that much when you add it all up. In contrast, as the river moves downstream, it has sediment added from tributary 1, tributary 2, and tributary 3. And they are all going to be adding more and more material to your river. So the total amount of sediment your river is carrying is getting higher and higher and higher as you go downstream. Now, the highest sediment load is going to be at the delta. And when the river, of course, hits the delta, it slows down and it starts dropping sediment. And so that's why, if you look at this diagram here, the mouth of the river doesn't actually have much of a sediment load because most of it's being dumped here in the delta. If there was no delta there, then your sediment load would keep getting higher and higher and higher, and then you see a sudden drop off at the mouth of the river when the river velocity slowed down and the sediment had to be deposited. So the final thing is the maximum sediment grain size. What is the biggest size of particle that your river can move? Well, in this case, it's the reverse of the other four. It's actually going to be highest up here towards the headwaters. Why is that? Well, remember, in the headwaters, the water is dropping quite quickly. Okay, dropping quickly under gravity. So that means the water may not have the highest velocity, but it does have the highest energy. And so that means your water can actually start moving around much larger particles than your river can down here, because your river down here may have higher velocity, but it doesn't necessarily have higher energy. And so what we have here is a situation where we have all the energy of the river is focused into one small channel. So there's a lot of energy focused in that one very limited small channel. In contrast, by the time we're down here, our channel is very, very big. So that means you have all that energy distributed over quite a large volume of water. So you'll have more energy up here in the headwaters. So this is the region in which you can move the largest material, because obviously you need the more energy you have, the larger the material you can move. Okay, so let's just have a think about how the volume will change over time. Or should I say discharge will change over time. So let's have a quick look at these graphs here. So these graphs are referred to as a hydrograph, and they plot discharge over time. So what do we tend to see? Well, on a very broad scale, we will see discharge change on a season scale. Okay, typically spring and fall will be wetter than summer and winter, and so on a broad scale, you'll typically see discharge go up in the spring and the fall, and you'll see it drop in the winter and the summer. On shorter timescales, however, changes in discharge will typically be a result of rain, precipitation in some kind. So what do we have here? Well, this is our hydrograph, and we can see this is where we have our storm. Now remember, as soon as you have the storm, the discharge isn't going to go shooting up straight away. The water has to travel over the surface of the earth, or it has to move through the soil, and then it makes it into the river. So discharge will tend to rise over a period of time. So discharge goes up as the water from the storm slowly enters the river. Then we have the peak flow. That's when the maximum amount of water from the storm is entering the river. And then once you're past that maximum, you're going to see the discharge, or the flow, discharge will decrease until you return back to your original flow level. So discharge increases after storms, not straight away. There'll be a bit of a lag. Then you'll hit the peak, then you'll return back to normal discharge. So this is a quite normal, straightforward, unspectacular hydrograph. So let's have a look at these two hydrographs down here, because they show something slightly different. So they're going to show us essentially what happens when the speed at which the water makes it into the river changes. So in this graph here, you can see we have the blue peak and the purple peak. So the blue peak is a situation where you have water entering the river very, very fast. So your thunderstorm happens and the water is being deposited into the river very, very quickly. So this tends to happen in areas where you have very steep terrain, so the water is running down the surface of the terrain very, very fast. Or it can occur in areas where you have lots and lots of concrete or asphalt. That obviously stops water going into the soil, and so it forces that water to move across the surface of the earth. And so what we see is the discharge will rise very, very quickly, because the water from that storm is being forced into the river very, very fast, so that the discharge increases very, very quickly, and then it also drops off very, very quickly, because the water has been pushed through very, very fast, and then it will return back to its base level. In contrast, where we have a situation where we have a basin with more gentle slopes, well, the water is flowing into the river more slowly. And it can also be a situation where we have less urbanization, so less cement, maybe more trees, more grassland. That helps to slow down the rate at which water enters the river. So in these kind of situations, what you're going to see is you're going to see the storm happens, and you're going to see the discharge rises more slowly, the peak is lower, and then it returns back to its original flow. Well, should I say original discharge. The one thing you'll notice though is, although the height changes, the width of the peak also changes. So when you have a storm in a steep basin or in a basin where there's lots of urbanization, you'll see the amount of discharge goes up very, very quickly, but the peak is nowhere near as broad, so the discharge moves through the system a lot quicker. In contrast, where we have a basin with a more gentle slope or less urbanization, so more grassland and trees, that allows the water to move into the river more slowly, so we see the discharge doesn't increase anywhere near as fast. The peak discharge is nowhere near as high, but the peak itself is considerably broader because the water takes longer to move through the system. Okay, so that was that. So I think this is a really good place to stop, so we're going to stop part 2 here. So once again, get up, have a walk around, go get some water, cup of tea, cup of coffee, relax for a few minutes, and then come back for part 3.